All right, everyone, find your seats. Welcome back. Today, we're going to try a little experiment, little time travel.
Ooh, I like the sound of that.
I want you to just transport yourself back. It's September 2nd, 1859.
Okay, so Victorian era. We're talking top hats, steam engines.
Exactly. And the absolute pinnacle of human technology is the telegraph.
Which was, basically the Victorian internet is the only way to send a message faster than a horse.
Right. So imagine you're in a telegraph office, Boston. It's late at night. The air feels heavy.
And the operators are looking a little spooked.
They're confused. Yeah, their machines, these brass keys and sounders are just going wild. And we actually have a transcript of a conversation from that night.
Between Boston and Portland, Maine.
It reads like something out of a ghost story, really. The Boston operator taps out a message.
What's he say?
Please cut off your battery entirely for 15 minutes. He's telling Portland to physically disconnect the power.
Now, in any normal circumstance, that kills the circuit. No power, no message.
Yeah.
That's rule number one.
But that's not what happens. Portland replies, "Will do so. It is now disconnected."
Okay.
And then Boston taps back. "Mine is disconnected, and we are working with the auroral current. How do you receive my rating?"
Wait, with the what?
The auroral current. And Portland's replies the amazing part. He says, "Better than with our batteries on."
So they're running on nothing.
They're running on the sky. For 2 hours, they sat there and just chatted with no man-made power at all. The atmosphere was so charged, it was surging up through the ground wires and running the machines.
And this wasn't just a quiet little phenomenon. I mean, operators were getting electric shocks.
Nasty shocks right through their fingers. Telegraph pylons were throwing off sparks. In some places, the paper tape they used to record messages actually caught fire.
This was the Carrington Event. It's still the gold standard, really, for a geomagnetic storm.
And that's why we're here. This isn't just a history lesson, it's a warning about what's sitting right over our heads. So that's our topic today, the Carrington Event and the physics of these solar storms. We're going to break down what the sun is doing, how these explosions work, and, the trillion-dollar question.
What happens if 1859 happens again?
Right. Because the stakes are completely different now. In 1859, a telegraph goes down, a message is late. Today, it's a magnetic avalanche hitting a world that runs on electronics.
Our entire global infrastructure.
So let's start with the anatomy of this thing. We always hear solar flare and CME thrown around, often interchangeably.
Yeah, and that's a common mistake.
Yeah.
They are very, very different. The best way to think about it is like an old cannon firing.
Okay, cannon.
When it fires, you get two things. First, you get the muzzle flash. That's the solar flare.
The flash of light?
It's a brilliant flash of light in X-rays.
Yeah.
And because it's light, it travels at the speed of light. So from the sun, that's 8 minutes.
So by the time we even see it, it's already hitting us.
It's already here. It causes radio blackouts on the sunlit side of Earth. It's disruptive, for sure, but it's just the flash. The real problem is the cannonball.
Which is the coronal mass ejection, the CME.
Precisely. A CME isn't light. It's stuff. It's matter. A huge cloud of magnetized plasma shot out into space.
And since it has mass, it's much slower.
Much slower. Usually takes a few days to get here. But when that cloud, that cannonball, slams into Earth's magnetic field, that's when the chaos starts. That's your geomagnetic storm.
So the flare is the warning shot, the CME is the impact.
That's the idea. And we have a scale for those flares, kind of like the Richter scale for earthquakes.
Based on X-ray brightness, right?
Exactly. You start with A, B, and C class. They're basically background noise. Happen all the time, don't really affect us.
Okay.
Then you get to M class, medium. They can cause minor radio blackouts, maybe a small radiation storm at the poles. But the top of the food chain is the X class.
X class. Even the name sounds serious.
It is. And the scale is logarithmic, so an X1 is 10 times more powerful than an M1. And it just keeps going. And X2 is twice an X1, and X10 is 10 times an X1.
I remember seeing the data from that huge storm in 2003. There was a flare so intense, it broke the sensors.
That's right. The GEOES satellite sensors just maxed out. They cut out at X28. Scientists went back and estimated it was probably closer to an X45.
An X45. It's hard to even imagine that much energy.
It's billions of hydrogen bombs going off at once. It's staggering.
If you are enjoying this video, please watch it until the end. It helps the channel a lot and encourages us to continue our work.
It really does. So the question is how? How does a giant ball of plasma generate that kind of force?
Right. This gets us to the engine of it all, this idea of magnetic reconnection.
It is the engine. You have to imagine the sun not as a smooth ball, but as this tangled mess of magnetic field lines. And because the sun's equator rotates faster than its poles,
Everything gets twisted up.
like rubber bands, they twist and braid and store up enormous amounts of energy.
And eventually, you twist a rubber band too much.
And it snaps.
Hmm.
On the sun, these field lines get forced together. Lines pointing in opposite directions get shoved close, they cross into an X shape, and then violently they break and reconnect.
And that snap releases all that stored magnetic energy as heat and motion.
Instantly. But here's the thing that puzzled scientists for decades. The old theories, like the Sweet-Parker model, they predicted this should take thousands of years to happen.
But we see flares erupt in minutes, so what was missing?
Chaos, basically. The breakthrough was understanding something called plasmoid instability.
Plasmoids. Sounds like sci-fi.
It kind of does, but what it means is that the sheet of electrical current between the magnetic fields isn't stable. It stretches and breaks apart into a whole chain of these little magnetic bubbles, or plasmoids.
Okay.
And that fragmentation allows the reconnection to happen exponentially faster. It's not one slow break, it's a cascade, a magnetic avalanche.
That's a great way to put it. A small trigger causing a massive system-wide collapse.
And we've seen it. The solar orbiter spacecraft actually saw what are called raining plasma blobs. Yeah. After the explosion, you see this superheated plasma cool and just rain back down onto the sun's surface.
Wow.
It's proof that this avalanche model is what's really going on.
So let's take that physics back to 1859. We know it started with an observation by two astronomers, Richard Carrington and Richard Hodgson.
Total coincidence, they both saw it. It was around noon, September 1st. Carrington was sketching sunspots.
By projecting the image, right.
Right. And suddenly, he sees these two patches of intensely bright white light just appear. A white light flare.
Which is super rare. You usually can't see them without special filters.
This one was so powerful it was visible against the sun's own brightness. And then 5 minutes later, they were gone.
And Carrington was pretty skeptical. He had that famous quote, "One swallow does not make a summer." He wasn't sure if that little flash he saw could cause all the chaos on Earth.
He couldn't have known about CMEs. But the connection became pretty obvious pretty fast. The auroras were just unprecedented.
Normally, you have to go way up north to see them. Alaska, Norway.
In 1859, they saw them in Hawaii, Cuba, Colombia, right near the equator.
There was that story from the Rocky Mountains of gold miners waking up at 1 in the morning.
Yeah, they started making breakfast because the sky was so bright they thought the sun was up.
And people in the Northeast could read the newspaper at midnight just by the red and green light in the sky. It's incredible.
And that brings us to the speed. We said CME normally takes a few days to get here.
But the Carrington CME arrived in 17.6 hours.
Insanely fast. And the theory is that it had some help.
There was another storm a few days before.
Exactly. On August 29th, that first smaller storm acted like a snowplow. It cleared out all the ambient solar wind, all the particles that are normally in the way.
It cleared a path.
It cleared a path. The Carrington CME had a wide open highway all the way to Earth.
Okay, so that's 1859. Sparks, glowing skies, confused miners. But ultimately, life went on. If that same event happens tomorrow.
It's a completely different story. We're not talking about telegraphs anymore.
No, we're talking about the electric grid. The estimates for a Carrington-level event today are, what, between 0.6 and $2.6 trillion.
Trillion with a T. In the U.S. alone, it's a staggering number.
So what's actually breaking? Why does a magnetic storm take out a power grid?
It all comes down to something called GICs, geomagnetically induced currents.
Okay.
When the CME hits, it shakes Earth's magnetic field. And a changing magnetic field, as we know from physics, induces an electrical current in any conductor. In this case, the conductor is the Earth's crust, the ground itself.
And electricity wants to follow the path of least resistance.
Which is not the dirt. It's the miles and miles of highly conductive power lines we've strung up everywhere.
So the current comes up out of the ground and into the grid.
Exactly. It enters through the neutral ground connections on our biggest transformers.
The huge ones you see at substations.
Right. And those transformers are built for alternating current, AC. But these GICs are a form of direct current, DC. And when you pump DC into a transformer designed for AC,
it's bad news.
It's very bad news. The core saturates magnetically, it overheats, it starts to vibrate violently, and eventually it melts or burns out.
And you can't just pop down to the store for a new one of those.
No. These are custom built, they weigh hundreds of tons, and they can take months, sometimes years to replace. If we lost hundreds at once, You're looking at blackouts that last for months.
But there are solutions. This isn't just a doom and gloom story. Let's talk about the neutral blocking device, the NBD.
This is a really clever piece of engineering.
Yeah.
The idea is simple. If the bad current is coming in through the ground wire, you have to block that wire.
But you need the ground wire for safety for the normal AC system to work.
Right, that's the trick. So the NBD uses a capacitor bank.
A capacitor.
In simple terms, a capacitor blocks DC but lets AC pass right through. So you put this device in the neutral line, and it acts like a filter. It lets the grid operate normally, but when that DC current from a solar storm tries to get in, it hits a wall.
And this has actually been tested.
It has. They put one in a substation in South Dakota. And in February of 2023, there was a moderate G3 storm. The device worked perfectly. It sensed the rogue currents and blocked them 4 separate times during that one storm.
So we have a shield.
We have a potential shield, yes. But we also have to realize that Carrington might not even do the worst-case scenario.
You're talking about the Mayak events, going further back in time.
Much further. We could look at carbon-14 in ancient tree rings. It's a proxy for cosmic radiation hitting the atmosphere. And we see these massive spikes. One around 774 AD, another in 993 AD.
How much bigger are we talking?
The 774 AD event was likely 10 to 20 times more powerful than the Carrington event.
20 times? I can't even imagine what that would do to our modern world.
It would be catastrophic for the grid. And there's another danger, especially as we start moving off planet, radiation.
For astronauts on the moon or Mars?
Right, we're talking about solar particle events, or SPEs. This is when the explosion accelerates protons to almost the speed of light. Outside Earth's magnetic shield, that is a lethal dose of radiation.
It would cause acute radiation sickness.
Absolutely. And that's why understanding the physics is so important. There's a concept called the spectral knee.
Okay.
It's the point on the energy graph where the number of high-energy particles drops off sharply. It basically tells us the maximum energy the shockwave can produce.
So it tells you how strong your storm shelter needs to be.
Exactly. It's the difference between building a shield that works and one that doesn't. It's life or death for future space missions.
It really puts our whole existence in perspective. We think of the sun as this constant, friendly star.
And it is. It sustains all life here. But it is also a dynamic, magnetically furious, incredibly violent object.
So to recap our lesson today, a flare is the flash, a CME is the cannonball.
One disrupts radio, the other disrupts everything else.
We learned about magnetic reconnection, the avalanche that powers these explosions, and that the Carrington event, as big as it was, might not be the biggest punch the sun can throw.
And crucially, that we're not helpless. We have the physics, we have engineering solutions like the neutral blocking devices.
We just have to choose to implement them. The 1-in-100-year storm isn't a question of if, it's a question of when.
And our technology has made us so much more vulnerable than the Victorians ever were.
It leaves you with a final thought, doesn't it? We spend all our time looking down at these little screens, relying on this invisible flow of electricity.
But that whole world exists at the mercy of the star we orbit.
Maybe we should all spend a little more time looking up.
Just, remember to use a solar filter.
Always use a filter.
If the listeners enjoyed the lesson, they can subscribe to the channel, turn on the notification bell to be informed about new videos, press the like button, and share the video with colleagues, as this helps us maintain the channel. Thank you.
Class dismissed.